Here's 2.3 lesson. So how do you get stuff to react? They have to meet up. They can't react if they're not together. So they have to collide. They have to have enough energy to do it. That depends on what they are, the shape of them, and so forth. And they have to be in the correct orientation. If they have to go head to head, then head to tail doesn't work, side to side doesn't work, and so forth. So you got to go head to head, then anything else is wrong. So what you got to do is bang them together often enough and hard enough to get this really moving. So that means if you turn up the heat, things tend to react faster. Because what is heat? Heat is energy. Heat is motion. In fact, I would take a note. Temperature is the average kinetic energy, moving energy. It's the average moving energy of the molecules you're talking about. So if you turn up the temp, you're turning up their energy, which means you've got more energy here. They're colliding more times per second with more energy, which means you might get a correct orientation with enough energy in a collision more times per second. It reacts faster. Also, you could pour in more of the stuff, of course. You could increase the pressure. If it's a gas, you could cram it together more. You could increase the surface area if it's a solid. You might try putting into YouTube something like blowing flour through a flame. I've done it. It makes a mess on the counter. I've done it in the lab, but you can get a pretty good little fireball going if you just take common flour and give it a big puff through a Bunsen burner. Flour will burn, as you've noticed if you've left something in the oven too long, and if you let it go through an open flame with lots of oxygen between the little particles, you can get a little fireball going. That's because there's so much surface area. The oxygen is contacting the little pieces of flour very well from many different directions. So you have a lot of collisions with the molecules you need, the wheat and the oxygen, the flour and the oxygen. And you gave it energy, right? And the orientation is random, but you bang them together hard enough and often enough, and you get what you need. So you increase the temperature and add a catalyst. And I would write this down. The catalyst is something supplied yet not consumed, which does a very special thing, which we are about to discuss. So here's our potential energy graph. So here's our reactant A, and here's our reactant B. Well, because here's A and B, right? So we start out with the reactants, and over time we produce the products. So this is time. And this is energy, which I wish they had labeled. I would go and label it if I were you. So the potential energy of the molecules is some amount. We're just going in very broad strokes here. So, for instance, the classic example is this paper. This paper does not sit around catching fire. Why? You have to get it heated. So you have to supply enough energy. You have to increase the energy of the paper enough to where it starts reacting with the oxygen molecules, which it's already in contact with, right? That's not the problem, that there's no oxygen. It's that you haven't activated them enough to get them going enough to make this happen. So you have to pump energy into the system almost always to get this going. Well, you always have to pump energy into the system, because if you didn't have to pump energy in, it would have happened already. Anything that's going to react with the ambient energy around you already did it. So that stuff's all used up a long time ago. So you're going to have to pump energy in. So here is the potential energy of the reactant. Here's the potential energy of the product when you're done. We're going to pretend it's all used up. All the A turns into B. Here's what we call the activated complex. So you heat the paper, it catches on fire, and it starts dumping out light and heat, doesn't it? And the energy of the paper goes down, as you all know, because it's hard to get anything done with the black soot left at the end, right? Right, that stuff is famously unreactive. It's literally just thrown out. The only thing I can think of that ashes are good for is maybe fertilizer, and even not really then, and making traditional soap in very old-fashioned ways, and not paper usually, but actual wood ashes from the fireplace. You can go look that up on YouTube too. Anyway, the energy came out, and then it's over. So how much energy came this is the activation energy. The energy you got to pump in is the activation energy, or energy of activation. Energy of activation, because we're nerds and we like to put things kind of backwards sometimes. And so this is the activated complex. When you're here, you have the activated complex. It is activated by getting the activation energy. So overall, how much energy came out? Well, the difference between what you started and what you ended with. And this is an exothermic reaction, and you know that because energy came out. And I think we discussed that a little bit last year, but exo means outside, like exoskeleton on a beetle, and therm means heat. So the heat came out. How can you tell? It had a bunch of energy and then it lost it. Where did it go? Where did it go? Energy cannot be created or destroyed. It was not destroyed, it escaped. The energy came out of our paper, didn't it? And it left. It went out. If you sort of turn this around, then, and if something went like this and ended up here, you would be pumping energy in. And if you had something, here, let's do this. That, you would have an endothermic because it ended higher than it started. You pumped energy in, and yet it did not release all of it back, and it ended higher than it started, and so energy went in. That's endothermic. So here's what the catalyst does. The catalyst, I said, is introduced by the human being or nature or whatever, but it is introduced, from outside the reaction, and yet it is not consumed. Otherwise, if it was consumed, it would be a reactant, wouldn't it? And what it does is it lowers the activation energy, which allows everything to get going a lot faster. If you only had to like rub paper with your finger to be catching on fire all the time, if the energy of activation was that low, you'd be in danger all the time, right? And so if we had a catalyst that was that effective, you just burn up your homework, by moving it around. But that would be the effect of a catalyst. It lowers the energy needed that you got to put in to get this reaction going. And that does come up on the test. How does an increase in temperature speed up the reaction? Well, we already discussed that. You bang more of them together with more energy, and so you're satisfying two of these things here. You can't govern the correct orientation, but if you bang them together twice as many times, you assume the correct orientation is going to happen twice as many times. Also, it's going to be even better than that, because when they bang together in the correct orientation, more of them will have the correct energy. So it's probably going to work even more than twice as well. Okay, I would go label this graph. They didn't label it, and that is confusing. And this does come up on the test sometimes. Here's the amount of energy. This is greater. Energy is growing. Number of molecules, of course, is growing. So here's the average kinetic temperature, the temp here, of our first amount of molecules. So do most of them have, let's look at the solid line, most of them have the threshold energy, the energy needed to react? No, only this amount does. Whatever amount exists under this line, then that's the amount that are going to get going. Anything back here, the molecules that exist back here don't quite have enough. Most of them only have this amount, right? There's a whole big bunch of them at this line, right? And fewer, the number of molecules is the Y. The number of molecules having more energy is decreasing pretty darn well. Now, of course, how many molecules have zero? Well, zero. I mean, that's stupid. That's zero energy is absolute zero. So this does not meet the corner. There is no such thing in this system as a molecule that has zero energy. They all have something, right? And it climbs pretty well. So most of the molecules are sitting around with this sort of energy in here, huh? Well, if you heat it, what happens? More of them have more energy. And so it's kind of like squeezing this bump here, and it squashes out over here. So the dashed line, the area under the dashed curve, represents the same number of molecules as before. We haven't changed that, but more of them have more heat. Look, the average is moved over here, right? Or the greatest amount. And that may not be the mathematical average. We don't mean that literally, but the greatest amount has grown from here, energy here to energy here. So that's an increase. And the number vertically of the molecules that have enough energy to get going this second has grown. So by heating it, we have increased the reaction rate because more of the molecules, vertical, have more energy to the right. Now, what does the addition of a catalyst do? Well, remember, we have to go and do something here. They didn't actually put this in. Oh, yes, they did. Here we go. Here's the catalyst, and this is the effect of the catalyst. The catalyst, remember, does not supply energy. It lowers the bar for the energy needed. So here's the effect of the catalyst. It takes the threshold energy and moves it over here to the left. Why does increasing the temperature speed up the reaction? We talked about that up there. So let's go on. I am skipping this. It does not come up on the test. I double checked. So multi-step reactions. So let's say we have a 3-step reaction. Go ahead and read this, hit pause. If the first step is the slow step and it's been determined that that's the slow step, then this is the rate determining step. And I think they use the word rate determining step on the real test. If, again, I would write this down, if the slow step is the first step of the multi-step reaction, then it determines the rate, like this. If Ford is trying to roll trucks out of the factory, right? Last thing they do is put on tires. I don't actually know, but we'll pretend, right? And then they got to get a driver, and they got to put gas in it, and then they got to get a driver and get it out. They got to go park it, right? All right. So the first thing they're going to do is put on tires because they're gonna roll it over to the gas pump. I don't know, but we're going to say that. If they're having trouble getting tires today, the first of those 3 steps, I don't care how fast they can pump the gas or how many drivers they have, the delivery of the tires is going to determine the rate of the trucks coming out. These are immaterial to the rate if you're held back at this step. This is the bottleneck. So this effectively makes the rate law. And if that's the rate law, then the rate law here would be rate equals K, of course, right? HBr to the first, because there's a 1 here, times O2 to the first. So this would be a second order reaction. HBr, whoops, there we go. We can ignore the effect of these on the rate because they're not the thing slowing us down. So what's the overall reaction? This, right? Let's prove it, they ask. Do these steps, in fact, create this overall reaction? So what you're going to do is take your intermediates and cross them out. So anything that is created and yet destroyed is neither a reactant nor a product, right? If it's created and destroyed, it's not really present except in the middle, in the intermediate parts. So what was created and yet destroyed? Well, this was created and yet it is used up. Look, it's destroyed, it's not there. So that's out, and it has to be on opposite sides, right? These 2 were created and yet they are destroyed. And also, to peek ahead, they're not in the overall reaction, are they? So 2 of these cancel out 2 of those. The 2 BRs don't seem to cancel anything. The 2 HBRs don't seem to cancel anything out. And in fact, this one adds to that one. This one adds to this one, adds to this one. So that's 4 of them, which is what we were looking for. Remaining is 1 O2 on the left, 2 H2Os on the right, and 2 Br2s on the right. That is, in fact, what we get. When we cross out the intermediates, we do get that. So this is at least a decent attempt at representing the multiple steps that could create this. So if these are examples of slow steps you could have, then of course, then again, the coefficient becomes the exponent. The coefficient becomes the exponent if the slow step is first. And so here are examples of possible slow steps, and then the coefficient becomes the exponent. So which step is the rate determining step? Step one, how do you know? Because it's slow. And look, there's the rate that I said. So here's the rate that I said, sorry. Here's the graph with 2 steps in it. So this one is harder to achieve, isn't it? It's higher. So this is going to happen at a slower rate. And apparently this happens first. This happens second because we're going time and potential energy, right? So the slow step is first. It has a larger energy of activation. Write the equation for the overall reaction. We cross out the intermediates, and the F singles are the intermediates. So we get one of these and one of those makes 2 of those, which is, 2 of these and one of those makes 2 of those. That's that. What are the intermediates? The F singles, the F1s. Are there any catalysts? Nothing was introduced that was then also regenerated, right, or that stayed in. All the reactants are gone at the stage of the products, aren't they? So there are no catalysts this time. Write the rate law for the overall reaction, and what can we do? We can say that the first step is slow, and therefore we can ignore the effect of the second step, and we can, for the purposes of the rate law, we can cross this one out. And then the coefficients become the exponents, and look, we have NO to the first, F2 to the first, and of course times K. So read through this, hit pause, and here's our example. So here's our overall reaction, and by experiment we've determined that it is a second order dependent on NO only. So it's KNO to the second. We're going to deal with 3 separate possible mechanisms and generate a rate law and see if it matches what we know is true because we did this in real life. And this is the rate law you get when you really do it. You don't just play around on paper. So if this is a slow step, we can cross this one out and we can say, if that's true, if this is the true mechanism, then the rate law would be this to the first, of course, times K. Is that what we found in real life? No, it's not consistent. This is not the true mechanism. Okay, this one is a bit complicated. Hit pause and do your thinking and listen to it 3 times or whatever. We have 2 steps, and the first step is not the slow step. So this gets a little mathy. So our fundamental rate law is based on this one, right? Except that, look, this, the first step is delivering this, isn't it? I mean, where else did it come from, right? The NO3 is being delivered here. So, yes, this is the rate determining step, but this step is also somewhat determined by this. I mean, if this can only deliver 5 of these, then this step is going to run slower than if this can deliver 100 of them, right? So you have to substitute in for this. How fast is this being delivered? Well, we said this is at equilibrium. And here's the point. If this is a slow step and this is the fast step, this one is trying to deliver the NO3 faster than it can really be given, right? So how fast can it deliver it? Well, I take it back. It's actually more dependent on how much of this is there. So how much of it is there is going to determine how fast this one ends up running. We're going to take this as delivered by that and say, yeah, but this depends on that. And it sets up an equilibrium. And if it sets up an equilibrium, what you get is KEQ, the constant of equilibrium, is equal to the products over the reactants, the molarities of, to the power of the number in front, the power of the number in front. So for this one step, the coefficients become the exponents. So this one, invisible one, becomes this exponent here, and this one become the exponents here. But what I want to do is I want to substitute in for this. How can I substitute in logically and mathematically in a way that's true? Is I can use this. And that's what they're saying here. So when we solve for NO3, these multiply over, and NO3 is mathematically substitutable as this. So let's take this and put it in for this. Then I have the NO3 becomes this, and I have something that's true. Now we consolidate. NO times NO is NO squared. Any constant number times another constant number is a new constant number, whatever that is. And the O2 wasn't affected. It doesn't multiply cleanly by anything, and so it remains its own molarity there. So we have generated the rate law if this is the true mechanism. Except this rate law doesn't match the one we got back when we did it in real life. So this is not the mechanism. In mechanism 3, if this is the slow step, we can mentally cross out this one. It won't matter. The real driver of the speed is this, and if that's true, then the rate will be k times this molarity only to the power of the number in front. So the 2 here becomes the exponent here, and you know what? That is the rate law that we found when we did it in real life. So mechanism 3 is our winner. That appears to be what happens in real life, or at least it sure matches the rate law. So you could have various kinds of catalysts, acid base, and here, what's the catalyst? And I had to stare at this a little bit, but a catalyst is introduced and yet not consumed. So also, I need to make this point real clear. It is not something, just something that scratches out. Yes, I could go and scratch this out. Oh, look, it's left and right. So I could go cross it out. But you know what? This was not generated by the reaction. It is not a product that is then consumed. It's not an intermediate. It was introduced initially, and yet it is not used up at the end. It is regenerated or not used up. So this is a catalyst. What's the catalyst? It's the sulfuric acid. The sulfuric acid is the catalyst. And so really what we do is we go and write that like H2SO4 over the arrow and maybe put cat as a catalyst. We tend not to actually include it in the reaction. That gets a little weird. It's a product and a reactant, and it's kind of neither. It's a catalyst. If it was introduced and yet not consumed, and it's present at the end. And that would be an acid base. So heterogeneous would be out of phase with the other ones in a different phase. And this is kind of what's happening, the kind of stuff that's happening in your catalytic converter in your car. I understand they've got it better, but it used to be platinum-coated beads. So that would be a solid affecting a gas because the platinum is a solid. And so the platinum is introduced, and yet it is never consumed. So the platinum is the catalyst. And here, I really had to stare at this one for a moment, but the Fe3 is introduced, and yet it's not consumed. So the Fe3 plus, which I guess is delivered by this protein enzyme, is the catalyst.